Yoni Nazarethi here from 1 on Epsilon. We're in the second meeting of Math Teachers Code. We'll be speaking today about random numbers, about pseudo-random numbers, and even about the normal distribution. I'll try to look at the comments as I work, so feel free to interject or ask anything, suggest anything, or anything like that. So before we get to the actual content, let's go into JuliaBox. So I'll log in a sec from JuliaBox so you see it here in the start. So that's JuliaBox. If you haven't done this before, head on to one of our other videos where we show how to log into JuliaBox. It's rather simple. In this case, I'll log in via my email, and this will be Math Teachers Code. Key in my password. I've pre-registered before, so I already have an account with JuliaBox, and those of you that have done this previously have an account already with JuliaBox, and then I will launch JuliaBox. Okay, we're working in the Julia programming language as we saw last time. This is a language that's both fast to code in and also very fast in terms of runtime. It's a new language. Version 1.0 was actually just released this year. It's been under development in the past decade, essentially. So I'm waiting here for JuliaBox to launch, and this is we're using the free service by Julia Computing. You can also install Julia locally and run it locally on your machine, but I find it quite easy to use JuliaBox. And this is a Jupyter notebook, as we've seen in the previous time. This is the last notebook that we had, Math Teachers Code session number 1, and we'll create a new notebook in Julia 1.0, and we'll call it Math Teachers Code session number 2. So Math Teachers Code session number 2. That's the name of the notebook. I've renamed it up there, and we're ready to go. Well, what I'm going to do is I'll show you in about 1 or 2 lines what we plan to do for this whole session, and then we'll actually break it apart and go line by line. So I'm going to use a package. I'll do using PyPlot and also the statistics package. So that comma separates what I'm using. So this this command here that I've put in line number 1 includes elements from the PyPlot, that's Python plotting actually, and the statistics package into the namespace. Now, without explaining too much, what I'll do is I'll create data, and this data is going to be the mean, which is a sample mean, applied to the to one random variable for nothing. This is for nothing in 1 till a million. Okay, so this is a bit much because we haven't explained this yet, but you'll see a bit later on what I'm doing. What I'm doing here is I'm taking the mean of a single value. In this case, a single value is just a random value between 0 and 1. That 1 says it's a single value, and that's going to be our data. And I'm now going to plot a histogram of the data with 200 bins. So the first time I run this cell, so again we run cells in JuliaBox by doing a shift enter. The first time I run this cell, it took Julia a few seconds because it actually compiled some of the elements from PyPlot, the histogram. But what you see is a histogram of 200 bins. That 200 is the number of bins. If instead of 200 I would have had 10 bins, then we have only like 10 bins. Or I can also have 1,000 bins, and we'll have 1,000 bins. So it divided the data up to the range of the data from 0 to 1 to 1,000 or 200 or whatever, and plotted the bar chart saying how many elements fall in each bin. We're going to get to this in a much slower sense in a few minutes, but I just want you to see first the main point. So this is a uniform random variable between 0 and 1, what we might call a completely random value in a sense. Let me also add here a feature to the plot, which is norm true, which just means that the axis doesn't show the total number but rather the relative frequencies, so it normalizes the total number. Now instead of rand1, what I'm going to do is I'm going to do rand2, and before I do that, let me go up here and show you what rand1 did. Rand1 gave us one random value. In this case it was this number between 0 and 1. As opposed to that, rand2 is going to give us two random values. Okay. So once I'm going to change the bottom cell to rand2, what we're going to get is a mean of two random values. The mean of two random values between 0 and 1, and let's plot the histogram. So now we don't have anymore a uniform distribution. We rather have this triangular distribution. And this is something that if you think about perhaps with your students as you explain statistical concepts or the Central Limit Theorem that we're going to speak about later on, you can actually figure out that you get more values around the center, around 0.5, because it is likely to have a combination of a high value and a low value. It is more likely to have a combination of a high value and a low value as opposed to just a high value or just a low value. So this triangular shape can be reasoned out in that manner. You can also derive it in certain ways, but that's out of our scope at the moment. So again, rand1 was a uniform, but the mean of two rands was a triangular distribution. Well, what are we going to get when we get a mean of 3 rands? So let's change that rand to 3. Whoa! So that looks pretty much like what we might call a bell curve or a normal distribution. Now, we actually know that it's not a normal distribution. The normal distribution is a distribution whose density is always strictly positive, even if it's very, very small. So you can get any possible value, even though the values decay exponentially fast to 0. Whereas this one, we actually know that the mean of 3 random values between 0 and 1, the mean is at the minimum 0 and at the maximum 1. Still, it kind of looks like a normal distribution. In this specific shape, you can actually do a bit of rather complicated mathematics and see that it is a combination of 2 piecewise or 3 piecewise parabolas, I should say. That's what you get. That's effectively when you do something called a convolution of 3 uniform random variables. But we are not going to go there. Let's just go and get to the random of 4, and we get something that looks even more normal. Okay, so what I did here was a very quick demonstration that didn't really step into the details of the code. I rather used almost the minimal number of lines of code that I would need. If I want to be even more minimalistic, I can even take this thing here, which is called a comprehension. We didn't speak about this comprehension yet, and stick it here and call like n a number, so, and then put this n1. So say if I was doing this in front of a class and I was telling to the class, and I also put a semicolon here at line 3 to suppress this output, which is unneeded output that comes with the histogram plot. So these 3 lines of code, if I come to a class like this and just show this to a class and say, hey guys, alright, you've got now a uniform random variables between 0 and 1, but what if you take 2 of them? You take the mean of 2 such random variables, and I'll put this here, and n is 2. So now you've got 2 uniform random variables, and their mean will have this triangular distribution. And if I go for 3 uniform random variables, I get something which looks more normal, and 4 random variables will get me even more normal, etc., etc. So this is one of the highlights of today's meeting, creating such a thing. But I wanted to show a sneak preview of it first before we actually get to construct this from slightly more basic principles. So for that, we'll actually discuss the concept of randomness. So I'll create a cell above here, and I want to go to some old blog post which we've had in 1 on Epsilon, and this is called Are These Digits Random? You can look for this blog post. Are these digits random? So in this blog post, what we discuss the concept of pseudo random number generators. Okay, and we're going to create one ourselves. Not a very complicated one, but we're going to create one. So what do we mean by that? So if you remember last week, we spoke about a sequence which was the hailstone sequence and spoke about the Collatz conjecture, and in that case the sequence had some let's say chaotic behavior where it was jumping between values, but it's not really a good sequence to use for generating random values, for generating values that appear random. Now, what do we mean by values that appear random? Well, we're speaking about values that would be uncorrelated between one value and the next value, and we'd also want them to have, say, a uniform distribution over the range of values. And for this, there is a whole field of pseudo-random numbers. So when I use the rand function in Julia, it uses Julia's built-in pseudo-random number generator. In this case, it's probably the Mersenne twister. That's kind of a top-of-the-line pseudo-random number generator. But we're going to do something much simpler. We will go and use this thing called the linear congruential generator. And it is nothing but a sequence which follows the following set of rules. It is a sequence of values xn where the next xn plus 1, is some constant a multiplied by xn plus a constant c. So that is a linear, or effectively an affine transformation of xn, all modulo m. All modulo m. Now it turns out that if we choose good values of a and c and m, so a good triple ACM, then this sequence has good enough features that make the values appear quite random in the sense that we want, meaning they'll be uniform in the range of values 0 to m, or to m minus 1, and they will be rather uncorrelated. Not really, there's actually a very strong connection between xn plus 1 and xn, but they'll have good enough statistical properties to do some basic statistics. This used to be the generator that was used in a lot of software, and some old software perhaps still uses this, but new packages like Julia and many others would use something else. So let's go ahead and create this ourselves. So instead of using the Julia rand, we're going to create a function which we'll call myrand. Okay, myrand. That is our goal. So we'll do a function myrand, and this function is going to return, and this will be random values. That's what this function is going to do. But on our way to creating such a function, let's do it step by step. So the basic thing that we have is the value of x. This is this x, which is the x in the sequence. So let's say we just start in some arbitrary x. Let's start with x 2001. That is a rather arbitrary x. Then we want to set the constant a to be something, we want to set the constant c to be something, and we want to set the constant m to be something. And again, I'm hitting escape and L to see line numbers so I can speak with you about line numbers. Okay. So we've got A, C, and M. Okay. Now, what A, C, and M do we choose? So there are quite a lot of results in number theory dealing with these types of congruential, linear congruential number generators, and we're not going to get into that, but I'll rather go in the Wikipedia page into a list of parameters in common use. and some number which is just relatively easy to remember is this one, but we don't have to use this one, so we're going to use the multiplier a to be 69069, c to be 1, and m to be 2 to the 32. Let's go back to Julia box. So a is going to be 69069, c is just going to be 1, and m is going to be 2 to the power 32. So in that case, the given in x, the next x is just going to be a times x plus c, and if you remember from last time, we actually used the modulo function. This is the remainder of division by m modulo m, and I'm putting these parentheses here over the ax plus c just to ensure that this is done before modulo m. I think actually that modulo, if I wouldn't do that, it would do c modulo m first. Okay, because modulo would have a higher order of precedence over the plus. Okay, so if I run this cell, then we see that we moved from an x 2001 to some next x, which is this x, completely different x. Okay, I guess at this point I could do next x2, which is like the second next x, which is going to be nothing but a times next x plus c modulo m. Right, and now our next x2 is this value. I can print all three values. I'll put x comma next x comma next x2, and that actually creates a what's called a tuple in Julia, a 3 tuple having the values x, next x, and next x2, and we'll see them all printed out. So we start at 2001, we then hop to this number, and then we go to this number. Okay, now clearly we're not going to do this again and again and again and again and again. We'll rather implement this type of thing in our function myrand, which will give us the sequence of x's. Now notice that this is a deterministic sequence. A sequence in itself is not a random sequence. It's just called a pseudo-random sequence. And being a deterministic sequence, it depends on the initial condition, this initial x. So if I would change this x to be, for example, 1987, and run the cell again, then I get a completely different sequence. This initial x is often called the seed in the language of pseudo-random numbers. And actually, let me go here to Julia's built-in rand. So look, if I do a rand, comma rand, comma rand, I'm in cell 24, I get a sequence of 3 random values. I'll run the cell again and I get a completely different sequence. Run the cell again and I get a completely different sequence, etc. But in Julia also you can set the random seed. I'll set it to be something like a number, like this number 1987, some arbitrary seed. And now, oh, I see srand's not defined. So srand was, okay, so in Julia 0.6 there was srand, but I see that in Julia 1.0, so I typically use Julia 0.6, but this is Julia 1.0. So in Julia 1.0 I see that srand's not defined, so let's overcome this quickly and we'll go to the Julia documentation. And go to Julia docs. So this is a live error. So I'm used to using srand to set the rand. Oh, and it might be that I think I kind of remember in Julia 1.0, it might be that I need to do random, but I'm just going to search for srand. The Julia docs. So this is Julia docs. This is not the thing you have to use. There are a bunch of easier tutorials. But no, I didn't find it. Just like that. Okay, but let's go to base.rand function, search base.rand. So here is rand, and I'll search on this page for seed, generator, creation, and seeding. Okay, so I see that in Julia 1.0 they changed it to random seed, random.seed exclamation mark. Let's just try this. random.seed exclamation mark 1987. Okay, and I believe that I need to use a package random. Okay, and that probably worked. Okay, so at least from this little fudge up, you saw that, okay, I rather quickly went to the Julia documentation, I searched for rand, and then I searched for seed, and then I saw an example where random.seed is used. But I also remembered that something that happened between Julia 0.6, which is what I usually use, to Julia 1.0, which is what I want to use in this Math Teachers Code series for you, is that if you want to do anything with randomness that's more than the very basic use of rand, then you need to use package random, as we did here in line number 1. So that's random.seed exclamation mark. The exclamation mark is part of the function name, because that actually signifies that it's changing something in the system, and it's changing the seed to be 1987. Now look, if I run cell 30 again, look at these values, 0.95, 0.56, and 0.03, etc., etc. If I run the cell again, I'm going to get the same values. So this is the random seed in the system, whereas if I change it to a different seed, I'm going to get a different set of values, which is again reproducible for that same seed. So line number 2 here is in a sense similar to line number 1 here. This is our manual seed, and this is the built-in Julia random seed. Okay, back to our function myrand. What are we going to do with our function myrand? So let's give the function myrand a seed. That is going to be an argument that will go into the function, and let's also give it an n, which would ask the function to create such a number of random values. Okay, so in the first line of the function implementation, so now I'm implementing the function. So in line number 2, we'll say that x is going to be the seed. We'll start with a seed. And then we'll actually want to iterate on lines like this next x and next x2 n number of times. So we will do something like for I in 1 to n, we're going to do n iterations. And a key line here is going to be x equals a times x plus c modulo m. Okay, and let's actually insert these values of ax and m to the function. So I'll put them, look, I'm going to take lines 2, 3, and 4, which are here, and I can actually write them in one line of the function. You can do this in Julia. You can do a comma c comma m equals 69069 comma 1 comma 2 to the power 32, and that just assigns a to be the value 69069, c to be the value 1, and respectively m to be the value 2 to the power 32. Okay, let's not finish our implementation, but just do something intermediate and return a value of x here. So what we have here is a function myrand, and I'm going to do shift enter. And if I now try and also apply this function, I'll apply the function myrand on, say, the seed 2000, running for 10 times. I'm going to get some other value which came after application of 10 iterations of line number 5. So line number 5 was iterated 10 times. But that's not exactly what we want to do. What we want to do is we actually want to store the values of x and then return a list of such values. So for this, let's create an array. Let's call it array, and let's do this by using the zeros function on, say, int 32 and for n. So let's see what this does before we use it. So I'm going to do question mark zeros. Okay. So zeros is also a common MATLAB function. It's a way to initialize an array. So if you do 0, if you see in this example here, you see if you do 0 1, it creates a 1-element array, and it actually takes by default, it's going to be of type float 64. Okay. If you do zeros and you say the type and you say like 2 dimensions, 2, 3, it's going to actually create a matrix. Okay, and there's all kinds of intermediate things, such as if we do zeros, and in this case I'll do an int32, so that's a 32-bit integer, and I'll say, let's say 10. So what we get is an array of 10 32-bit integer zeros. Now actually I think this int32 is a mistake. We should probably go for a float, and I'll show you why in a second, but if we go to float 64, then we get floating point numbers. You see 0.0, etc. So let's change this to float 64. And here we want to, in this line, line number 7, we want to put the random value in the array. Okay, in this line we want to put the random value in the array. So what is a random value? The random value is x, right? Now we can access the ith index of the array. An array is a list of numbers, and we can access the ith index by going ri, because this for loop from line 5 to line 9 iterates n times, and in each time I gets a value 1, 2, 3, 4 up to n. Keep in mind, in Julia, unlike languages such as JavaScript and C and Python, array indices don't start at 0 but rather start at 1, which in some ways is more natural and in some ways less. But anyway, that's what it is. So here we'll say array I equals x. But instead of putting array I to be x, let's actually put array I to be x divided by m. Now what does that do? So look here, let's go back to this cell and run it just so we see it run again. This is x, next x, and next x2. What if we call this thing, we'll call this whole thing, we'll call this tuple. That's a tuple of x, next x, x2. And now let's do tup divided by m. So, sorry, we'll do tup dot divided by m. So now we're going to take each value in this tuple, and I'll do tup comma tup dot divided by m. Okay, this is, so in line 7 we created a tuple which was our x, next x, next x2, and that is this tup. These are these things that I'm highlighting, and they're of types integers. They are integer types. Then here what we're doing is we're dividing each element by m. Now this dot slash says to apply the division by the single value m to each element of tuple. Okay, that's why before when I try to do tup without the slash, I get an error and it says no matching method for division of a tuple by a float. But if I do a dot, that works. Now back to the idea, what we do here is we're actually renormalizing the values. Instead of lying between the total range which they can be, which is 0 up to m minus 1. Okay, so the values can be in the range, let me make a markdown cell as I explain this. Values can be in the range 0 to 2 to the power 32 minus 1. Now here I did a markdown cell with LaTeX. I'm mixing a few things today, just so you see. So this is, if you don't know what LaTeX is, don't worry about it, but if at the moment, but if you do, then you can see that I can also format LaTeX in markdown. I didn't do this last week. So the values can be in the range 0 to 2 to the 32 minus 1 because the linear congruential generator works on integer values. That's what it does. Once you've got the values between 2 to the 32 minus 1, then if you then divide by 2 to the 32, you get values in the range 0, 1. Okay, so when we use the built-in function of Julia, the rand function, it gives us values in the range 0, 1, which it guarantees to us are pseudo-randomly uniformly distributed in the range 0, 1, if I should say. Here, if we would take our linear congruential generator and divide by m, then we're going to get values that lie in the range 0, 1. So back to our function myrand, which is our built-in attempt. Okay, this is, I'll make this a markdown cell again. So this is our attempt, our try at a random number generator. Okay. So let's see this. So in line 8, what we did is we actually took the x, we divided it by m, and we've put that in the array. And then what needs to be the return value in line 10? Well, that needs to be the whole array. And we could have actually just not had the return statement. The last line in a Julia function is a return value. But to be a bit more verbose, let's do that. So let's run this. And now if I get myrand 2010, where 2000 was an arbitrary seed, I get 10 random values, which, well, I don't want to say that they're uniformly distributed between 0 and 1, but they were generated by this linear congruential generator. So let's not go for 10, let's go for a big number. Let's go for 1,000,000. Julia is fast and it can do 1,000,000 no problem. We don't get a printout of a whole million random values, it just shows us the first few and then these dots and then the last few. Okay, so we can call this data. Data is a myrand. So if, for example, I'll ask what is the length of data? Length of data is 1,000,000. So let's do some sanity checks on this data to see that it's at least behaves like something which would be like this thing. I mean, we're trying to emulate this thing, which is uniformly distributed between 0 and 1. So for example, let's calculate the mean of the data. So if we've got 1,000,000 values and they lie between 0 and 1, we would expect the mean, if it's uniformly distributed, to be half. So one way to do this would be to actually sum the data and divide it by the length of data. Okay, that is the arithmetic mean. So line 14 is here the arithmetic mean. But we can also use a built-in mean function. For this, in Julia 1.0, we need to do using statistics. And then we could use here, once we've done that, if I do question mark mean, you see the mean is, you get examples, but you can apply 2 lists of values and it will give you the arithmetic mean. So the mean of data, and we see that the mean of data is very close to half, 0.4997. Now if we get a different, and this is reproducible, every time I rerun this cell, every time I rerun cell 57, I get the exact same mean because I get the exact same million values, 10 to the 6 values, which were calculated. Now if I change the seed, and even if I change it slightly, I get a different set of values, and hence I get a slightly different mean. But statistically we see that this mean is still about half. Okay, if I wouldn't get 1,000,000 values but would rather only get like 100 values, 10 to the 2, then the mean can quite significantly differ from half because I only have 100 samples. But with 1,000,000 we're very close to half. Okay, let's do some other sanity check. How about the variance? So this is something, if you don't know what the variance is, you can continue watching this even without fully following, and if you do know what the variance is, then let's go for it. So let's actually write this in markdown here. So the variance of a data set is sum I1, I'm now writing in LaTeX, n of x I minus bar x, I hope this bar works, squared, and all of this is divided by n minus 1. That's a sample variance. Let's see if this worked. Yeah. Okay, so the variance of a data set is this. Okay, that's the sample variance of a data set, and if we now apply the variance function on data, we're going to get this number. So what this is, it calculates the deviation of each observation from the sample mean, squares it. If all observations were exactly equal to the sample mean, we'd get a variance of 0, but otherwise we get something a bit different. And we also divide by n minus 1, that is averaging it all. It's kind of like dividing by n. The n minus 1 is a bit of a statistical artifact. It ensures that this is an unbiased estimate for the mean. That's not so critical. Let's just use a variance function, variance of data, and we get this value here, 0.083. So what is this variance? Well, for this actually, if we now think about the variance of a uniform 0, 1 random variable, this is something that you can compute with calculus. And if this is beyond what you're interested in or not your thing, then again just skip this bit, but basically let me write what it is. It's going to be the integral from 0 to 1 of x minus half squared dx. The variance is actually going to be this integral for a random variable that is theoretically uniform between 0 and 1. Okay, the variance is going to be this, and you can actually calculate this, and it's going to be just 1 over 12. So for a uniform random variable 0, 1, the variance is 1 over 12. So that you can calculate this integral explicitly. It's nothing but an integration of a polynomial. Good. So what's 1 over 12? Let's put here another output line, and let's just put 1 over 12. And the third one is going to be the theoretical variance. I'm commenting that as a theoretical variable. So 1 over 12 is exactly 0.083, and the sample variance appears to be not so far. Okay, so this gives some indication that these random values are at least uniformly, or I say at least uniformly, between 0 and 1. It doesn't mean that they're random. There can still be correlation between them, and there certainly is, but at least in terms of their behavior, they seem to have the right mean and the right variance. Okay. Now it's time to use our histogram function, which is actually a rather complicated plotting function. So let's add here PyPlots again. PyPlot, not plural, singular. So I got a mistake, argument error, package PyPlot not found, because I had an S. So I'll delete the S, PyPlot. And the way we can plot is a histogram is we do PLT : hist. It's rather weird notation, but that's what we do. We're using the hist attribute of the plot object in PyPlots, and we apply this to the data. Okay, so let's just do that. And what this does, it creates a histogram of the data on the range of the data. The range of the data is 0 to 1. Okay. If you're actually interested, before I do that, let me comment this, and let's do minimum data and comma maximum data. You see, the minimum value is like this 5.7 times 10 to the minus 7. That's scientific notation here. And the maximal value is almost 1. Okay? So those pseudo-uniform random values that we created span most of the range between 0 and 1. And if we, again, run the plot of PyPlot. By the way, after PyPlot there's all this kind of junk, so if you put a semicolon here it suppresses the output associated with that and just creates a graphic. Then we get our histogram. Now a parameter that you can give the histogram here is a numbins. Okay, and I'll just set it as a variable numbins, and let's say we create 100 bins. Okay, so what this histogram did, it actually partitioned the interval 0, 1. I said this before at the start of the meeting today, but it partitioned it into 100 bins, and for each bin it counted how many occurrences of data appeared in that bin, and that's a view of the bins. Okay, yeah. So if you make it 1,000, you're going to get something that's a bit more jagged, because you only have 1,000,000 values. So 1,000,000 values, 1,000 bins, there's about 1,000 elements per bin, but then you see a bit more variability in the bins. So maybe 200 bins is a good setup. Histograms are not unique plots of data because they depend on the bin allocation. And yeah, that's all I'll say about it now. So these were our built-in random values. So having done that, let's now experiment with the central limit theorem again, and let's do it in a bit of a slower manner than what we did before. So we've got at our disposal our function, which we created from scratch, that we're proud of, and that's the linear congruential generator. We use these specific constants. Sometimes if we choose the wrong constant, so not any set of constants would work well, because it'll mean that the function won't have an incredible period. It might skip a lot of integers between 0 and m-1. But these ones are known to be good. So with this myrand function, let's go here to a new cell. I'll create, the way again I create new cells, I hit escape on the keyboard, that's a Jupyter thing, and then I hit the A button, for example, and that creates a new cell above where I was. So again, if I do myrand, then let's just call our seed. Let's call the seed 1957, and that's just an arbitrary thing. Myrand seed, 10 values. We've got our 10 random numbers. So let's call this now data 1 is going to be this array of 10 random values, and that's going to be with the seed 1957. Now let's take data 2 to be myrand with a completely different seed. Okay, so to get a completely different seed, what we'll do is we'll maybe just do let's just call the seed 2. So we'll call the seed 1 comma seed 2, 1957 and 2008. I somehow like to choose years for seeds, but that's completely arbitrary. So that's going to be seed 2 and data 2, another 10 values if you'd like. So you can put them together, data 1 comma data 2, escape else, so you see the line numbers, shift enter to run, and you see this is data 1 and this is data 2. Okay, let's change this 10 to be a meaningful number. We'll let that be n, and we'll actually let that be 1,000,000 values, or the number million, and then when we put n here we get 1,000,000 values. So data 1 and data 2 will be these 1,000,000 values. Now if I do plot hist of data 1, and let's just again set the num bins, let's set 200 bins, num bins. So that's a histogram of data 1. And if I'll do another one of data 2, if I just do this for data 2, I get a histogram of data 2. It effectively looks the same. But now what I'm going to do is something different. I'm going to do data 1 plus data 2. Now what is data 1 plus data 2? Now in Julia you can treat arrays also as vectors, and you can add them element-wise. So you're adding the first element of data 1 to the first element of data 2, and the second element of data 1 to the second element of data 2, the third element of data 1 to the third element of data 2, the fourth element of data 1 to the fourth element of data 2, etc., etc., up to 1 million times. So this new thing is actually the sum of data 1 and data 2. Now this is a point where often when I do this type of thing in front of students in class, I pause and I ask them to think, and I ask them to ponder what this new histogram would look like. You've seen it at the start of this tutorial, but let's say that you haven't seen it before. So I ask, what will this histogram look like? Okay. Now, when we try to think about what it looks like, well, one thing to think about at first is what is the minimal value and what is the maximal value. So what is a minimal value that data 1 plus data 2 can have? Well, it's 0 plus 0, and that's 0. And what is a maximal value? Well, it's 2. So we're not going to get anything greater than 2, right? Because data 1 is at most 1 and data 2 is at most 1. So the sum of the two datas is at most 2, element-wise. Alright, so if it's between 0 and 2, then comes the question, what shape does it have? And that's not immediately obvious, but once you plot it, you see that the shape is this, again, triangular distribution. And then there's often this awe in the class. And you look at the students' faces and they start to think, and they start to, why is that, and why is that, and why is that? And then you reason out that getting values around 1 is more plausible, because to get a value around 1, you can have one element being big and the other small, and that can happen with in multiple ways. Whereas to get values around 2 or around 0 is not so plausible, because you need both elements to be very large to be around 2, or both elements to be very small to be around 0. And that's how you get this triangular distribution. But then I add data 3. So let's do that. And I'm just doing it in a hard-coded manner, data 3. So before I hit Shift Enter, and I'll put a semicolon here also to suppress this output, but before I hit Shift Enter, I ask the students, hey, what is going to be the minimal value? And they say, well, 0. What's going to be the maximal value? They'll say 3, because that requires getting a high uniform here, and a high uniform here, and a high uniform here. So we're going to get something between 0 and 3. What's going to be the typical value? So the typical value, this is still the plot for only data 1 plus data 2. The typical value was 1.5. Sorry, was 1. What's going to be the typical value here? And then 1 or 2 students will realize that it's 1.5 because it's someplace in the middle. Well, it's right in the middle between 0 and 3. What's going to be the shape? The students think and scratch their head, and it's not so clear. And then you hit Shift Enter, and you get a mistake. So why is that? Data 3 myrand sin 3, and you have, and that completely kills the lesson. But then actually, when that happens, I can make a joke or two, and things often work out. So why is this? Attempt to access 1957-2008 at index 3. So where is the mistake? So when I get such, I actually have no idea what's happening here. So, well, I saw it, but let's say I still didn't see it. Okay. So what I'm going to do is I'm going to just comment this out and delete this and run again and see that there's no mistake. Okay, and there's still a mistake, so it's not this line. And then I kind of see line 1. Okay, so it says this error. Top level scope at in81.1, it says attempt to access 1957-2008, which is actually this tuple at index 3. So we forgot here seed 3. Okay, and then I realize what the mistake is, and I put this new seed, and redo things again. Okay, now mistakes do not kill my lesson. I mean mistakes, I mean coding mistakes of this type. They actually interject something. So I'm back with the students. Suspense, data 1 plus data 2 plus data 3. And I'm going to hit Shift Enter. And then appears this bell-looking curve. And then this bell-looking curve appears. And that's the magic of the Central Limit Theorem. So, and then I tell them about the Central Limit Theorem. So the Central Limit Theorem. Given a sequence of random variables, and to be technical they need to be IID in the basic Central Limit Theorem, independent and identically distributed random variables, and these random variables are x1, x2, etc. Okay, that's the Central Limit Theorem. I guess I didn't need those dots here. Okay, I'm writing here in LaTeX, and that's completely not important for the purpose of the coding, but you might as well see it. So given a sequence of IID random variables x1, xn, take Sn to be the sum of I1 to n of xi. Okay, so Sn is the sum of these random variables. Then frac Sn minus the expected value of Sn divided by the square root of the variance of Sn is approaches a standard normal distribution. This is a loose statement of the Central Limit Theorem. Let me fix this. The frac of Sn Esn square root, or Sn, another bracket missing here in my LaTeX code. Okay, so given some random values, if you sum them up, and then if you take the random variable, which is that sum normalized by the expectation divided by the square root of the variance, then you get a standard normal distribution. And there's a few caveats. This is not a precise mathematical statement per se, but it certainly doesn't matter for, it's I think good enough for K-12 math education description, but let me just fill in the little blanks. So this approach means that this random variable, this sequence of random variable, converges in distribution to a standard normal distribution. That means that the distribution function of this converges to the standard normal distribution function. There's also another caveat. The random variables must have actually a finite variance. So some random variables don't have finite variance, but that's typically something that we won't cover. So the point is that when you add up random things, you get something that looks normally distributed. Okay, and if you'd add a fourth data point, data 4, it would get closer and closer to the normal distribution. So that would be the data 4, and let's let data 4 be another sequence of data starting with a different seed, and now we'll get something that's even closer to the normal distribution. Now just to close off, let me actually plot the density of the normal distribution against the density of this curve, and let's see that the two densities kind of agree, and they tend to agree more as we add more and more data points. Okay, so those data points are those Sns. So for this I'm actually going to define a function here. Let's do it in a new cell, and let's call it f of x. It's going to be a one-line definition of a function, and it's going to be the standard normal density. So that is 1 divided by the square root of 2 pi, that's a number, times the exponent of minus x squared divided by 2. That's a standard normal density. Okay, so I could also write it here in LaTeX if you want. So f of x, the standard normal density, is frac over 1 over square root of 2 pi times e to the minus x squared over 2. Something like that. Let's see if that works. And I'll put this in a dollar sign here. So this is a standard normal density. Okay, that is the bell curve, the normal distribution, the Gaussian distribution. That's a density with mean 0, variance 1, centered around 0. This 1 over square root of 2 pi is just a normalizing constant, ensuring that the integral of this from negative infinity to infinity is 1. So that's a standard normal density. Okay, with this being the standard normal density, let's see how to plot it. So let's call x grid values between, say, -3 in steps of 0.01 to 3. That's a grid of points. We used this last time. This is a range in Julia. Okay, x grid. And then we can plot. Plot comes from PyPlot. X grid, comma, f applied to x grid. So this is rather advanced in terms of programming shorthand notation for applying the function f to every element of grid. It's kind of the broadcast operator. That's what it's called in Julia. Let's accept it for now. So this is going to plot the normal density. Now it would be great to get this plot up here above this plot. Okay, but there's quite a few steps we need to do to make that work. So first of all, this plot below is not normed, so let's add normed equals true to the histogram plot below, and that just normalized the values. Okay, so the grid without it, the y-axis had the wrong values, so that did that to the plot below. And we can actually, let's be ambitious and just take these 3 lines of code from above and stick them here below and see what happens. Well, it looks kind of okay, but certainly not, because this normal distribution, the f here, is a standard normal distribution, whereas this one here is not a standard normal distribution. Now, the way we wrote the central limit theorem here, we spoke about the normalized version of the sum, but we can now just create a new function g of x, and let's call it g of x mu sigma. And what it's going to be f at x minus mu divided by sigma. So it's a centering of the x times the normalizing constant 1 over sigma. Now this is, and I'll show you in a sec. So and you know what, instead of giving mu sigma, let's do it like that. Mu sigma f, I have a bracket missing, fx minus mu over sigma, there's an extra bracket there. That's g mu sigma. Okay, now when I plot, I'm going to do a y vals is going to be g of x at some given mu. So let's say mu is 1 and sigma is 1 for x in x grid, and we'll do this more in the next meeting, better plotting methods, but I'm going to plot here the y vals. So these y vals are going to be the g function, which is a composition of the f function and the transformation x minus mu divided by sigma multiplied by 1 over sigma, and that's going to be the y vals. So see what happens here. Gx1, x in x grid, it doesn't like what I did, sigma not defined, I changed sig and sigma, so let's call this sig and sig. And let's change the grid to be between y0 minus 10 and 10. Okay. Now we still don't seem to have exactly a fit, right? Because we don't have the correct mu and sigma. But we know what we want mu and sigma to be here. We want mu here to be the mean of 4 values like that. So that's should be 2. And we want sigma, that's actually requires a bit of analysis, but that's actually going to be 4 divided by 12, or the square root of 4 divided by 12. So this is the standard deviation of a sum of 4 uniform random values. And let me now change the range here to be between 0 and 4 again. And there we have it. So in those last few minutes I did things a bit quickly and slightly sloppily, but basically what we did here is we plotted here this second plot command in line 14 plots this normal density against the density of the histogram, which we have. And that's the central limit theorem demonstrated. You certainly don't have to do everything we did here for demonstration. You can simply go and you can run this 3-liner thing, and it's pretty much going to be the same thing, right? I just wanted to show you some of the coding components. And I think I'll stop here. I'll just remind you that I'm Yoni Nazarathi from 1 on Epsilon. I'd love it if you go to our website, register with us. That's in 1onepsilon.com. Register. You register up here in the top right. This way you'll get updates from us on what we do. And please give us feedback on Epsilon Stream. So Epsilon Stream, our web app, iOS app, or Android app. You can basically key in anything in the world of mathematics, for example the normal distribution, and get a few results that our team has selected for you, which we think are the best results for understanding that specific concept. Thanks so much, and bye bye.